We can't hear you.
I don't know if you can hear this, but my son is singing in the next room. He's terrible. He's terrible. Okay, dominant negative. So I think that fact is more important to me than the experiment they do in your book with it. Um, basically, knowing how this dominant negative works, and if I give you a question based on it, you'll be able to figure that out. But this is what they did. Basically, they added dominant negative type 2 receptor for activin, which knocked out all BMP and XNR activity. And when that happens, you get no dorsal structures, you just get ventralization. Okay, so again, showing how important these factors are. So here they are. Xenobus nodal related. I think in the book they just call them nodal related. 1, 2, and 4. Derriere, which is I'm forgetting now. I think it's a Wnt blocker. I can't remember now though. I'm sorry.
I
So
have a quick question
you want to
again.
what?
I have a quick question again. I'm a little
Oh,
confused.
mhm.
Did you say no?
I'm sorry. Go ahead. What?
Actually, so Activin, I mean, I haven't heard Activin like throughout.
Yeah.
And then suddenly we use Activin receptor to knock out BMP4 and XNRs.
Right.
So I don't understand what exactly it does.
Yeah.
And I mean,
Yeah.
yeah.
Good point. Good point. I think Activin's involved in development, but it's not one of the major players. But
Okay.
it goes through a TGF beta like pathway. So
Okay.
its type 1 receptor is very similar to the type 1 receptors for BMPs and XNRs and everything else.
Okay.
So by making that dominant negative for the activin receptor, you can knock everything out. And they
Right.
even from time to time, I'm not sure why they do it. I'm not sure why they're doing that instead of using, one of the nodal relateds or one of the BMP4s or BMPs or something.
Hmm.
Comes and goes. But
Okay.
what you need to know about it is it's a TGF beta like hormone, and it's used more experimentally. I think it is in the embryo, but experimentally that's what they're using a lot of the time.
Okay. All right.
Okay.
So does it knock the BMP and the XNRs by cutting off the kinase?
Yes.
Okay.
Yes, because in that TGF beta pathway, you've got the type 1 receptor and the type 2 receptor.
Hmm.
Both have kinases in their cytoplasm. And
Okay.
when they get activated by the hormone, they bunch together, and then one domain phosphorylates the other domain,
Phosphorate.
phosphorylate
Okay.
each other. So when you've got a type 1 domain, a type 1 receptor that's truncated, they still bind together, but now type 2 has nothing to phosphorylate, and it just stops there. It doesn't, the transduction
Okay.
doesn't go on.
Got it. Thank you.
Okay, so growth factors involved in mesoderm induction. I'm saying again, your nodal related, your BMPs, VG1, and activin. These are all TGF beta like hormones. Okay, now this gets a little repetitive again. Okay, so what these things are doing is upregulating brachyury. So brachyury then is our mesoderm signal. When we see brachyury, we think mesoderm. At least I do. And this is talking about you also get FGF at this point. FGF is going to be upregulated by brachyury, and then you get this autocrine positive feed loop where FGF increases brachyury and brachyury increases FGF. And this makes sure that in the cells that are expressing brachyury, you keep a lot of brachyury being expressed there. So that keeps things mesoderm. And you get this tube of mesoderm around the embryo because of that. Okay, so going back to what we talked about already, you've got your vegetal cells that are inducing mesoderm here. And in this area over here, you've got a big, over here, you've got VEG-T and beta-catenin, which gives us CMWA. So that gives us NuCoop here. NuCoop increases XNRs, which then affect the mesoderm here and upregulate the transcription factor goosecoid. And so goosecoid turns this into the Spielman organizer. And it does that by causing it to release, so this is what I just said. Okay, you're all of these guys. And then, oops, that's spelled wrong. Should be SIAMOR. Increasing XNRs produces goosecoid. And now because of goosecoid, you're going to get a concentration gradient of BMP4. Talk about that in a second. So this now is just talking experimentally again about how we know that concentration gradients can produce a pattern in a series of tissue. So this is talking about animal caps exposed to activin. Again, TGF-beta like hormone may even be going through BMP and XNR receptors. I don't know. But anyway, they're using it experimentally here to activate TGF-beta signaling. At no activin, you get the animal cap just stays epidermis. At a medium amount of activin, you get brachyury, so that's mesoderm, middle mesoderm. And at high concentration of activin, which would mimic high XNR, you're getting goosecoid being produced. So that's dorsal. And you see the same thing here in this bead experiment where you've got beads with a small amount of activin in them, and it will diffuse away only so far. So you get brachyury because you've got XNR or TGF-beta signaling here. You put a high concentration of activin, it's going to diffuse further. And where activin is highest, you're getting dorsal mesoderm. And where it's kind of moderate, you're getting, again, your brachyury, which is kind of middle mesoderm. And where it's absent, it's staying ectodermal. Okay, so concentration gradient giving us patterning. And that leads us up to, I'll come back to that, to this, where your Spielman organizer then produces cordon, noggin, and follistatin, and those diffuse away from the organizer around the embryo, right, and up and down as well. And that's going to give us a gradient of BMP4 activity because these three things are going to block BMP4. And they're doing it physically by binding to BMP4 extracellularly, and then it's inactive. So here we are going around the middle, giving us a ventral to dorsal axis of mesoderm. Coming up here, and it's by blocking BMP4, it's going to allow this to eventually to become neuroectoderm. And down here, it's making the difference between dorsal endoderm, which will gastrulate and become a head process, versus vegetal endoderm, which is going to remain gut. Oh, look at this. This is pretty. So here's your cordon and noggin again. It's blocking this way, allowing neuroectoderm, and blocking this way, which means that this will be your anterior endoderm. And we'll see that in the next slide. Oh, and this kind of exacerbates that, gradient because cordon will grab BMP4 and shuttle it over here and then get broken down by a protease, ADMP, and then BMP gets released over here and just keeps going this way. So that's just making your gradient even better. All right, let's go back to FGF. So don't forget this. I don't want to have to go through it because it's there. There's nothing I can say about it except that. But remember, this is your FGF pathway, and it's all about activating MAP kinase, which then turns on transcription factors in different genes. So there's that pathway. Now this is again, it's like we just learned all of these molecular reasons why this is patterned this way. And now suddenly the textbook goes back to the 20th century. We can't get it out of the goddamn 20th century. So now we're showing that this is already patterned at this early stage and blah, blah, blah. So don't worry about that one either. Ignore that. Okay. Here, now this is important. Here at this stage, this is the blastula again, but we've got a Spielman organizer, so late blastula. This is setting up that dorsal ventral axis with the cordon, noggin, and follistatin. But you also have an AP axis being formed here, and that has to do with Wnt. So Wnt is producing this organizer, but then blocking Wnt is going to give us anterior structures, and allowing Wnt is going to give us more posterior structures. So these leading edge cells here are endodermal, but they're releasing Cerberus, and Cerberus blocks everything, every goddamn. I'm sorry, I'm getting a little punchy here. It's hard to talk in an empty room and still keep yourself interested. So anyway, these endodermal cells release Cerberus, and Cerberus blocks Wnt, and it blocks BMP, and it blocks X. And so when this gastrulates forward, is going to produce a gradient of Wnt blocking. So then Wnt ends up high over here and low over here, and that gives us this other axis, the AP axis. But this AP axis is not specified yet, but it's faded at this point because these cells will crawl this way and drag these cells with them. So this is your anterior endoderm, and then this will be your anterior mesoderm. Then this will be your dorsal mesoderm, which is going to be anterior to posterior as it crawls across. Et voila. See, I just went French on you there. Et voila. Sure, I spelled it, I pronounced it wrong. So here's your anterior mesoderm in the end, all the way at the anterior end, releasing Cerberus, giving you this gradient of Wnt. Here at the posterior end, you've got high Wnt, so you've got posterior structures. And there's your 3 axes. All right, so this is again talking about those axes. I'm running out of time, so I'm going to go a little quicker. But this is just kind of repeating the fact that this Wnt gradient is what gives us our AP axis. And then here are the two gradients going at once at orthogonal to each other, at right angles to each other. You've got your Wnt gradient here, low, high. And you've got your BMP4, which is high in the ventral and low in the dorsal. And again, we're going back to the 20th century. What's that? Do not, sorry. Maybe later, I'm almost done here. Okay, so this is showing when the neural tissue is being specified, and this is showing that experiment too. So read through that. If you've got questions, email me on it and I'll explain it. And we're back to this. And this is again, a positional, when is each position actually specified so that now it is that thing. And so they're getting to that situation. This is again, neural, the Wnt signaling, giving you patterning of the neural tissue. So it's patterning the mesoderm, but it's also patterning the neural tissue. So at the anterior end, you get brain, and then you're getting go down. And there's your final pattern. Okay, then we got zebrafish. Not a lot about zebrafish. I think I spent more time on it than I should have, and I didn't spend a lot of time on it. The main thing I think is important here for you to know is this 3-layer patterning here. It's another thing I find interesting. So closest to the yolk syncytial layer, you've got this mesendoderm, which is kind of a mix of both cells. And then you've got mesoderm in the deep layer, and deeper than that, you've got the ectoderm. And then you've got your shield region, which is the organizer, and that's coming up. And then you're getting convergence and extension. And so the shield region is there because of dorsal determinants, again, just like we saw maternally laid dorsal determinants. Difference is it's not affected by where the sperm enters, but for some reason, these dorsal determinants get pushed up to here, and that becomes the dorsal end of the embryo. There's your fate map. This is about the only thing I found interesting about zebrafish compared to xenopus, is remember over here we had that ectodermin that was blocking the mesodermal signal. Here it's something released from the endoderm that's blocking the mesodermal signal, which is kind of counterintuitive. So your mesodermal signal then is NDR1 and NDR2, same as xenopus really. It's XNR versus NDR, which are the same molecule. And each of these goes a different distance, and that's giving you a patterning here with a gradient patterning. And then you've got this bad boy here, which is lefty, blocking the spread of those XNRs. and that stops the mesoderm from going into the endoderm. Okay, just like ectodermin and FOX11E did. Okay, and that, my friends, is all you need to know for the exam on Friday. It's not much, is it? Seems like a lot. Okay, questions? We've gone over a little bit today, but I owe you any questions or comments. So the exam will be set up just like the last one, right? Bunch of objective questions, fill in the blank kind of thing. And then 4 essay type questions. I'm confused. Somebody's confused.
I have one last question for you, if you don't mind.
Okay, okay.
Yeah. So we said that the main purpose of FGF is to do the positive feedback loop and increase recurry, but then we have the FGF signaling pathway, and then it ultimately changes some transcription factors. So like
Mhm.
what are those transcription factors? Are they increasing
So,
recurry or something
so
else?
one of them is something that's going to bring up brachyury. Okay.
Okay.
So MAP kinase will activate transcription factors that will produce brachyury, but also it's going to be involved in some posterior patterning as well. So FGF, I don't know exactly which genes it's going to turn on, but it's going to be a posterior posterior signal.
Okay.
Okay.
All right. Thank you.
Okay. Any other questions?
I have a question. So this question is back on Wnt, right? So remember you said if Wnt is knocked out, beta-catenin is knocked out, and we would just have the Spearman organizer forming, right? But then
Sort of, but not quite. Hang on a second. So don't forget, yes, if you knock out the catenin, then you'll get no Spearman organizer. But you knock out Wnt, remember we still have some maternally laid beta-catenin and disheveled, which will bring beta-catenin up. So just knocking out Wnt might not do it, but blocking out the downstream effector, beta-catenin will do it.
Okay. But then, like, if you knock out Wnt, wouldn't that affect the concentration gradient formed or no?
Yes, definitely for the AP patterning, yeah. But that's a little bit later than the Spearman organizer part.
Okay, so I was thinking, like, how would I answer this on a test? Would I say, well, all right, so the Spearman might form, but the AP axis might not form, or like?
This is what I would say. Early on, to form the Spearman organizer, you need beta-catenin and you need veg-T, okay? That's going to give you your nuc-coupe, and the nuc-coupe's going to cause the production of the Spearman organizer. So if you take out Wnt, you still have beta-catenin because it's maternally laid, okay? Now, once you get that Spearman organizer, you go past the 12 division stage and you're starting to get transcription from the nuclei. Now you're going to need Wnt, okay? And so if you don't have Wnt after that point, then you've got a Spearman organizer, but you're not going to be producing any anterior structures, I guess, because, oh no, it'll all be anterior. You won't get any posterior structures because you don't have Wnt there.
Okay. Thank you.
Okay.
Dr. Slish.
Yep.
Since it's my birthday, can we have the test on Saturday?
No.
Come on, please.
You know what I did for my birthday? No,
What'd you do?
I worked.
Oh, that sucks. I'm sorry.
I didn't even get any presents.
But you can make my birthday better, bro.
I got a hearty handshake from my wife, and that was all. And I was
What are
happy.
you on, bro?
I was happy.
I'm sorry.
Once a year, I get a handshake.
All right.
No,
I'll do my best on the exam though, since it's gonna be for my birthday. So got you.
Okay, guys.
All right. Have a good day.
I'll go. All right, later, dude.
Bye.